So we're still trying to produce this tool that's going to be useful to us called the space-time diagram, where t is normally on the y-axis and the x, the distance or the positions, are on the horizontal axis. So it will turn out, it's not clear at this point because we haven't done any physics, it will turn out that the speed of light is an important speed, and so we will want to understand how a particle of light moves on the space-time diagram. And so if we start at x equals 0 and we produce, we turn on a flashlight and we create light, and we imagine light as little particles moving in space, then if we turn on a flashlight in this one-dimensional universe, we'll have particles of light that can move either to the right or to the left. And if they move, the ones that move to the right are going to be moving something like that on the space-time diagram. Now, of course, the speed of light is 3 times 10 to the 8 meters per second. So that's a large speed. And you could imagine tilting very much towards the x-axis because your spatial displacement is large per unit time, but it wouldn't be useful to us to have an almost horizontal line on this diagram. So we really want to make the speed of light obvious, and the most straightforward thing to do is to sort of imagine the speed of light as being a diagonal line, or halfway in between the two axes, so that we can think of a region that involves speeds slower than the speed of light, and the region where the speed of light is greater. And the region where the speed is greater than the speed of light, and a region where the speed is less than the speed of light. So, but there's nothing special about the origin. So if we generate a particle of light here at this position at that moment in time, then it'll go like that. If we're here, it'll go like that. The tilt is what matters. These all represent light traveling, or anything traveling at the speed of light, and we normally indicate that with the symbol c, right? So the speed of light is c. And if we think of this as particles launched to the left, then if we start at the origin, we'll have a diagonal line that has a 45-degree angle like that, where we can start anywhere on the space-time diagram, and we want a 45-degree angle between the t and the negative x-axis in this case, right? So all of these lines represent something moving at the speed of light to the left. But the key here to notice is that if this is time and this is x, a 45-degree line, which represents our speed of light, involves equal increments on both axes. So, 1 unit in t and 1 unit in x, and so on, 2 units in x, 2 units in t. And so the slope here, well, first of all, x over t is a speed, right? Distance over time is a speed, and we're dealing with the speed of light, so we're dealing with x over t is equal to c. But the y-axis has the t, so our equation looks like t equals 1 over c times x. And for 1 increment of t and 1 increment of x, right, that must hold. So this is telling us that c is just 1. So we're using units in which c is just 1. So the slope here is actually the inverse, right? T over x is 1 over c. So it's 1 over the speed. So notice that if we think of a slope that's greater than 1, in other words, more vertical than horizontal, then we are dealing with, more vertical than horizontal would be something like that, right? So the speed of light is like that, that's c. This is more vertical than it is horizontal. That represents speed, constant speed, slower than the speed of light on the space-time diagram. And if we have a slope which is less than 1, in other words, it's more horizontal than vertical, then it would be something like, say, that, right? And whereas the speed of light would be that. So this is, let's just keep going here. This would be c, and this, so this is speed less than c, and this would represent speed greater than c on the space-time diagram. Okay, so now we have a way of recognizing speeds that are close to the speed of light on the space-time diagram.